Okay, so HMMs. So what's a model look like for k-means? What's the graphical model behind k-means? Oh, I should clearly ask this on the exam. Yeah. Graphical model. We talked about Bayes nets that can be like, just you've got the circles and the arrows, and they can be in any configuration as long as there aren't cycles. It has to be a directed acyclic graph. So this can be anything. Or rather, I don't have them on here. Bayes nets can be anything. Naive Bayes is just this bunch of boring, non-connected variables because they're all assumed to be independent. K-means for mixture Gaussians, what's the graphical model look like for that? I'm really trying to stress that this year. I didn't talk about this so much in previous years. I just thought it would be a nice way to start class, but apparently it's not.
It's like two circles. It's the
Two circles? Yeah. One's above the other?
Yeah.
And there's an arrow going down from the top one to the bottom one.
What cluster you're in is the top one, but that's not
Score, yeah.
that affects your position.
Beautiful. Did anyone understand that?
When do we talk?
Like 3 different times. Yeah.
The one class I missed?
No. He didn't miss 3 classes. He just falls asleep a lot. That's okay. What's the model look like? It looks like this. I showed this picture a million times, right? This is the... and here's the naive Bayes. What's this? You're in a particular state, and then you go to the next state, and what state you end up in depends on what state you were in, plus you maybe have selected some action. What? Yes! Score! Now, class, what is this?
It's Markov. Right?
It is Markov.
It looks hidden.
It is. I'm hidden. I'm sorry. It's a hidden Markov model, exactly. So beautiful. Okay, hidden Markov model. So you got 2 aspects. You've got the state transitions, describing how the system works. The probability of being in a particular state is the sum over all previous states you might have been in. The probability of being in that state times the probability of transitioning to x sub t, given that you're in x t minus 1. And then, this is nice to know, but it doesn't do you all that much good because you can't see the states. All you get to see are these little bits of evidence, these little breadcrumbs that get dropped out of the spaceship that are conditional on what state you were in, luckily. So, what was the question?
What spaceship?
The one that goes around dropping breadcrumbs.
Okay.
I don't know. I guess I was trying to imbue the state with an aura of mystery. Okay. Yeah. Sorry. Okay. We'll come back down to earth for a second here. Did you ever know about the band Parliament? Bootsy Collins and George Clinton. Yeah, so crazy band. If you ever, you should look them up. Okay, so we're given the transition model and the sensing model, and now we're going to talk about the decoding problem for HMMs. There are a lot of different problems having to do with HMMs, like how could you learn one in an unsupervised way given bunches of data? How could you determine the probability of a sequence? But we're going to focus on the decoding problem, which is find the state sequence given just the observations. It's like, here are the breadcrumbs, where did the spaceship go? Or, here are the sightings of periscopes by deranged sailors, where are the subs? Or, here are the returns from your radar, where's the wall? Or, the Soviet threat or whatever. I don't know.
I'm actually going to ask, what form does E take? Like, what does it look like?
It could be, that's a great question. You could have all kinds of different observations. Today, we're going to talk about words, because somebody wanted to hear about natural language processing. So our observation sequence is going to be The blue bank closed. The blue bank closed. So you're a robot and you hear this. The blue bank closed. And you're like, oh, wow, I'm supposed to be a smart robot. I better do natural language processing on this and figure out what the hell it means. The first step in natural language processing is to figure out what the words are. And then we can figure out what the sentence means, because it does turn out that the meanings of sentences depends heavily on the words that are used. There are other things like, the blue bank closed! Or, the blue bank closed. You know, it does have different meanings, but we're going to ignore those prosodic effects having to do with intonation and just focus on the words themselves. So, the blue bank closed. So, blue, so the is a very nice word because it's just one thing in English. It's a determiner. It means like how many of them were there, and is it indefinite or definite, and the, it's like singular definite. So there's no ambiguity in the word the. But the instant we get to blue, you may think blue is pretty obvious, like it's the color of a shirt. But in fact, the wind blew. Blue could be a verb. The blue shirt, that blue is an adjective. Or it could be like blue is my favorite color. It could be a noun. So there's actually at least 3 different. So that's a different sense, a different meaning, but I'm just gonna worry for now about parts of speech. I didn't want to go there, but no, they totally. We should recognize that additional layer of ambiguity does exist, but I'm going to ignore it for today and just say we've got to decide whether blue is an adjective, a verb, or a noun. Yeah, but I'm going to assume that you have the phonemes perfectly. Yeah, the blue bank closed. And bank is a noun, and it's also an adjective, and it's also a verb. Like you can bank a turn, you can have a bank note, a note from the bank, or it can be the bank, meaning either the riverbank or the financial institution. So I'm ignoring the semantic distinction between financial institutions and sides of flowing water forms. Closed, as far as I can tell, is just either a verb or an adjective. The closed door, closed is an adjective there, or it could be a verb. So we see the blue bank, or so the blue bank closed, and period. And we'd really like to know what sequence of parts of speech we just saw. And I think you and I all agree that it's really determiner, adjective, noun, verb, but the computer doesn't know that. The computer sees 3 times 3 is 9 times 2 sees 18 different possibilities for this sentence. And we've ignored semantic ambiguity. So we have a 4-word sentence that can be interpreted 18 different ways, ignoring the more difficult problem. Just to give you a hint of why Matt doesn't get any sleep, because he's taking a natural language processing class. So I made a grammar of English. I'm sorry it's a little messy. Here are the different parts of speech. Determiner, adjective, noun, verb, and period. And my grammar of English is in the form of a Markov process. We can argue at some other time about whether that's the best model of English we could possibly come up with, but let's just say it's a fine example for today's class. And I say, okay, we can transition from a determiner to an adjective with probability 0.5. And with probability 0.5, we can go from determiner all the way to noun. Like you could say the book, or you could say the beautiful book. We don't know how to say the beautiful and intelligent book because we can't have and. We don't have conjunctions in our grammar. So if we transition to adjective, there's a 0.8 chance we go directly to noun, a 0.2 chance we go back to adjective, and then please forgive me, my probabilities don't add to 1. There's a 0.01 chance we go directly from adjective to verb. Now you might say, like, where do grammars like this come from? And what you do is you learn them from data. Like you go to the web and, I don't know, there are various techniques for trying to learn grammars. You pay graduate students. That's one way people learn grammars is you say, like, here's a lot of text. Please write down what the parts of speech are for every word. And like this is how people, many hundreds of people have gotten through grad school by earning money doing this. And yes, we should all feel sorry for them. So you can just go through this corpus and count how many, what came after determiner. And I even have some files on my computer of like, actually I've got, like 1 million words that have been tagged, like stories and all kinds of stuff. Very popular thing to do in the 90s. So anyway, so these probabilities come from like student labeled data. So they're always mistakes. So like it is possible you could go directly from adjective to verb, skipping the noun. But it's a low probability. It's 0.01. So then if you're at noun, there's some small probability that you could go back to adjective, or you could go to noun again, or you go to verb with probability 0.9. From verb, you can go to verb again, or you can go back to adjective, or you can go to period. And I put a lot of probability. I put probability 1 on going to period, but I guess I should have put 0.98 because I made little chances of going elsewhere. So anyway, so this is the grammar of English. Everyone understand that? This is how English works, and this is our sentence. And now I'd really like to know what the parts of speech are for those words. Now, what I haven't told you, I should copy this example down in a nicer way. Nope.
So if it was just a probability 1 of verb going to period, wouldn't that mean that there's only ever one verb in a sentence, and that's always at the end?
Yeah. Yeah. The blue bank. Oops, the blue bank. Blue bank closed. Period. Now we're going to have ambiguity in our lexicon here. So what we need is the probability of the observations given the underlying state. So we're wondering things like, let's see, and this could be determiner or adjective or verb or noun, and this could be noun or adjective or verb, and this could be verb or adjective. And we need, for det, the only thing you can get is a the. For adjective, you could get blue. So there's probably 1 of getting the. For adjective, you could get blue or bank or closed. So let's say there's a 0.4, 0.3. And then noun, we could get blue or bank. So let's say this is 0.4 and 0.6. I'm just making these up. For verbs, we could get blue, because it's really, we're hearing this, so it's blue, B-L-E-W. Or bank, or no, wait, yeah, or bank or closed. I think we're most likely to get closed here, so maybe that's 0.7, and that's, no. People deal with money a lot, so it's probably 0.2, 0.2. Where do you bank? Okay, so this is our observation model. So we don't know what states the system went through, but we know for every state what kinds of observations it's likely to give rise to. Okay? Everyone get that? So this is giving us the probability of the various bits of evidence given the underlying state S. All right? And then that grammar that I showed before, right there, this is giving us the probability of S prime given S. All right? So that's the two parts of an HMM. So now the question is, you're a robot, somebody says the blue bank closed, and you're wondering, gee, what parts of speech just went by? Let's figure it out. So we're going to use this very famous HMM decoding algorithm invented by a guy named Viterbi. He's so famous that the University of Southern California Engineering School is named after him, the Viterbi School of Engineering. And it's a great algorithm because in the length of the string, you would think that the possibilities are going to explode exponentially, but the Viterbi algorithm is not exponential in the length of the string. It's actually linear in the length of the string, which is very cool. It uses dynamic programming. Whenever you hear about exponentials coming down into polynomial land, you know dynamic programming is probably lurking in there somewhere. Okay, so there are a couple factors at work here, right? There's the probability of how often do adjectives come after determiners, and how often do nouns come after adjectives? What's the probability of a tag sequence? And that's given by the grammar. But there's also the probability of the words themselves. Like, if we just look at the grammar, then we won't be looking at what words were actually spoken. So we have to factor in both the way language works, what comes after what grammatically, and the actual evidence from the speech signal, like what words we heard and what do they provide evidence for, what parts of speech are they providing evidence for. If you heard bank, that's some indication of what part of speech it was. So we have to factor those both in to our calculations, and we're going to do that by multiplying them because they're probabilities, and probabilities love to multiply, just like rabbits. So the Viterbi algorithm is actually super simple, and I ought to grab a copy of it just to make sure I have one around. Does everyone have a copy of the algorithm in front of them? So we're just going to, and it's actually a little bit subtle, which is why I'm going to spend half the class talking about Viterbi today. We're going to make a lattice. Let me just sacrifice this piece of paper and show you. Make an offering to the gods here. So at any one time, you could be in one particular state. So here's t equals 0, t equals 1, t equals 2 at any particular time, and here are the states. So this is S0, S1, S2, S3, S4, S5. We don't know what state you were in at T0, but you are going to transition to a new state at T1. So it's like we take all the possible states and line them up, and we think about, okay, we're going to transition to a state at the next time step. The probability of being in a particular state here has to do with what states, how probable it is to get to this state from the previous states, and how probable we were to be in those previous states themselves, and the probability that if we were in this state, we would see the evidence that we got. So we multiply those three things together. So if you look in the Viterbi algorithm, we multiply, for every new state, we're going to try and find what's the most probable way we got there. I like to think of it actually looking backwards. The algorithm thinks of it as looking forwards. So for every s, we look at the s prime, but you can maybe think of reversing these. For every s prime, we're going to compare all possible previous states compute what's the probability. We're keeping a dynamic programming table called V, which is the probability of having been in a particular state at a particular time. What's the probability we were in S at time t, times the probability of going from S to S prime, times the probability we would have seen that observation at time t if we had been in S prime. So we multiply those three elements together. And we're just going to keep the biggest one. We're going to compute that for every possible S. We keep track of, for every state at every time, we keep track of the most probable way of getting there. And we actually have a parent pointer back. This should probably say S prime comma t here. I apologize for that. So we're keeping track for each state at each time step, what's the most likely way we got there? And for each state at each time step, what's the most probable way we got there? So you end up with this lattice, or if you want to think of it as a layered graph. Every time step, we keep track, what's the probability? Each of these cells is the probability that we were in that state at that time step. And when we consider the new time step, we say, well, what's the most probable way I could have gotten there? And what's neat about this algorithm is that we're keeping track of the probability for every single state. So we never decide once and for all, oh, at time step 1 we were in that state. Because it could be that later on we'll see some evidence that makes it very unlikely we were in that state. But we haven't considered that evidence yet. So we have to maintain all possible hypotheses about what state we might be in. And we keep working this forward for every state. What's the most probable way we could have gotten there, and what's the probability that we're there? And then at the very end, in your Markov process, there's usually some final state that you end up with. Or you just look at the final state. Let's say this was only a two-step process. So there were only 3 time steps. Then you look at the most probable state here, whatever it happens to be. Let's say this is the most probable one. And you say, okay, this is the most probable state we ended up in. We're actually keeping track. The probability of being here actually takes into account the probability of the most probable way of getting there. So the most probable state sequence ends here, and you trace back along these pointers, just like it's dynamic programming, right? So you have to do this trace back to recover the most probable sequence. Okay, so that's kind of a very abstract view. We're going to do the example so that you can see how this works in practice. But do people get like the hazy outlines of how this might kind of make some sense? And the key is we're multiplying the probability of being in some previous state times the probability we got to the next state times the probability of getting the observation given we were in the state. And we find the very best predecessor for every S prime. We're basically cycling over the S's here, finding the best parent, the best predecessor for S prime.
That gives you the most probable sequence?
Yes.
Does it tell you how probable that sequence is?
Yeah, that'll be this V score. These scores actually go down. I mean, we're always multiplying everything by things less than 1.
Right.
So they get nice and low as you get longer and longer.
Is that automatically normalized? Or would you have to...
It's automatically true. You don't even need to normalize.
Okay.
Yeah. The probability of a particular state sequence in an HMM, the longer the sequence, the less probable it is. So it all happens, all just works. Okay, so let's do the example. Let's see if we can do the example. Okay, so we have the blue bank closed. Okay, I'm going to need some calculator help, Matt. Okay, does everyone have the grammar handy? Does anyone write down? I wrote down the grammar. I'll try and fit all this on the screen at the same time. We'll see. It's not going to work. Well, then everything would be really small. Is that okay? Oh, okay. Phew. Thank you for the suggestion, Lee. Okay. So, so the nice thing is we start off at t equals 0. Everything is 0 except det. So we're wondering what state we were in. So we've got det and adjective and noun and verb. Those are the possible states we could be in. And at t equals 0, all the probability is at det. I'm just going to, by instructor's prerogative, initialize the HMM to that starting state. If you don't happen to know what the first word was, then you just make some magical mystery starting state with it has probability 1, and then the first transition is to the first word. But I'm going to save us one word by saying, it starts with det. And now we have to fill in the next time step. So t equals 1. So if we look at the Viterbi algorithm, it's saying for each next state S prime. So let's take det, and let's take the next state det. Okay, what? Yeah, how'd you compute that? Because we have to multiply the probability of being in the previous state, which is 1, times the transition probability, which is 0. Because if you look at our grammar, there's no way of getting from det to det. So the probability there is 0. So, okay, so the first time, so this loop in our Viterbi algorithm is looping for every S. We could look at all S prime. So when we look at S prime equal to det, we get a 0. When we look at S prime equal to adjective, what do we get? Who's next? Tyler, you're sitting next to Dylan. You remember the Viterbi algorithm? It's here on the slide. Here on one of these slides. It says we multiply VST, which is 1, times, so that's the probability that we were in S at... oh, that should be a t minus 1. I'm sorry. Oh, Matt, can you hit me on the head after class? Just lightly. Exactly. Times 0.5 times, I'll use x, times, and now what's the probability we would have gotten that observation, namely blue, if we had been in the state adjective? Exactly. Times 0.4, and even I can multiply these things. Okay, so our current score for here, for adjective is det, and we should draw a little arrow, because that's where it came from. All right, what about for noun? Det to noun. So we have 1. No, it's not actually. This is a 1, like a 1, like a unity 1.0. So I think we're just half of 0.4 is 0.2. Here we've got the probability of being in det is 1. The probability of going from det to noun is 0.5, and the probability of getting blue if we were in the state noun is 0.4. Okay, so everyone's really thinking that we're just as likely to be in a noun state as an adjective state, having just seen the blue. Verb is 0 because there's probabilities of 1 being in det, and the probability of transitioning from det to verb is 0. So that's 0. So that's nice. All right, so now t equals 2. We see bank. Oh, I'm sorry, we forgot to do the full iteration of Viterbi. The full iteration of Viterbi, we'd then say, okay, now pretend the previous state was adjective. Now, how probable is it to go from adjective to det? How probable is it to go from adjective to adjective? How probable? the thing is that the probability of being an adjective is 0. So all the other scores are going to end up being 0 for each of these. Okay, but it is an n squared process. I mean, for each of these, you have to look at each of these. So it's n squared in the number of states. So it's states times number of time steps. So Mr. Viterbi was smart in that he got it linear in the time steps, but it is squared in the number of states.
Are there more efficient ways to handle this problem? Or is this
You know what? Wow. This is the kind of thing I would ask on an algorithms final if we had a graduate algorithms class. So every time you have a dynamic programming algorithm, you can turn it into heuristic search. So people have applied A-star to Viterbi decoding, and they've applied beam search to Viterbi decoding. Just keep the top few candidate states at each level, like the top 10 or something. Because usually, even in speech processing, as ugly as speech is, usually the top K states are much more likely than the rest. I mean, for a real part of speech tagging, like if you look at the Penn Tree Bank, they have like 50 tags or something. So it's a large number. But only a handful of them are going to have significant probability. So maybe just keep track of the top few. So Matt is trying to get a scientific paper out of taking a dynamic programming algorithm and using best first search on it. We wish him well.
One more time, how do we determine the probabilities of
Each cell here? Don't worry, we're going to do 2 more time steps.
left, like the left column right there?
Oh, this? Where 1, 0, 0, 0?
Blue, like,
Oh, this. Oh, someone gives you this. You can look at some data if you want to figure it out. So, I have a file somewhere in my computer that's just det, noun, adjective, verb, just tags after tags, strings of tags. So, and they're aligned with words. So it says for every tag, we can just go look at all the words that happened to occur with that tag and count up how probable each of them was.
So in this case, are we pretending that that's a full dictionary? It's just
Yeah, it's a pretty impoverished version of English. But dude, I put it on one slide. Come on.
the dictionary only has to be the words you see.
That's true. If you are an agent operating in a world, why know anything else other than the things you... Well, maybe you want to imagine the Klingon language.
Yeah, but it only has like 600 words.
Oh, really? Okay. Piece of cake, then.
They're more worried about killing each other than speaking and typing.
Thank God. So is this clear? So this is, this is the knowledge of how the states evolve, and this is your model of the sensor, really. So you can imagine instead of words, these could be periscope sightings, and this could be the motion of how subs like to go and where they like to be. It really doesn't matter. Okay, we're ready for the next time step. So now we imagine being in debt. Oh, that's easy to imagine. Being in debt, being indebted, especially as a student. You imagine being in debt and going to debt, and the probability of that. And so this is all 0. So we fill in zeros all along here because there's 0 probability of being in debt at time step 1. And now we come here. And now we imagine being in adj and going to all the different states. The probability of being in debt and going to adj is debt and being in adj and going to debt is 0. There's no way to get to debt. Yeah, so this is going to be 0 for the rest of eternity. Now we're in adj and we go to adj. That does have some non-zero probability. So there was a 0.2 chance we were in adj, and then the probability of transitioning to adj was 0.2. And then the probability of seeing bank, if we were in state adjective, was 0.3. So this is 0.12, I think. And our best parent so far is there. And now we say, okay, we're in adj, and we went to noun. So the probability of being an adj was 0.2, and the probability of going from adj to noun was 0.8. And the probability of seeing bank if we were in noun is 0.6. Oh, I need help.
You check the first one also. The decimal place is not.
The decimal place is not correct here?
Yeah, it's
0.0. Thank you. Matt, where are we here? 6. All right, thank you. And our parent pointer goes back up to that cell. And now adj going to verb. Well, we had a 0.2 chance of being an adj. To go to adj to verb is 0.01 times the probability of seeing bank if we're in verb is 0.2. So I can just tell you this is like small. I'm going to just write epsilon. Okay, that's not going to, I mean, who cares? It's really small. Who cares what your parent pointer is?
This is not related to this course, but this looks a lot like sequence line.
Dynamic programming.
All dynamic programming?
Paching.
Things look like this?
Yeah. Well, no, but a lot of them look a lot like this. Some of them, instead of being a rectangle, are triangles, and some of them are cubes, and some of them are hyper rectangles. But the idea of filling in a table based on previous entries is pretty common. Yeah, nice observation. That sequence alignment is the thing Matt's working on. He's going to align DNA like no one has aligned it before, in circles. Okay, so now we've gone through det, we've gone through adj, now we go through noun, because noun also has non-zero probability. So the probability going from noun to det is 0, thank God. From noun to adj, so there's a 0.2 chance we were in noun. The chance of going from noun to adj is 0.01. And the probability of seeing bank if we were an adjective is 0.3. And we can already tell that this option is going to lose, right? This new option of getting to adjective in time step 2 via noun in time step 1, that is less probable than getting there from adjective. So we don't adjust the parent pointer. And there's 0 chance of getting there from verb, so great. Now we have to do this one here. So to get from noun to noun, so it's 0.2 chance of being a noun. Noun to noun is 0.01, so I feel another loser coming on here. Bank, while we're a noun, is quite likely at 0.6, but still we lose out to this path here. Okay. And then there's some probability we could have gotten to verb through noun. So the probability we were in noun is 0.2. To go from noun to verb is 0.9. And the probability of seeing bank as a verb is 0.2. So, Matt, I need to know what this is. It's like 0.03 something. 3.6, yeah, thank you. Okay, and that is having gotten to verb from noun. So we really have two hypotheses, really live ones at the moment. This one is fairly unlikely at 0.012, but this is 0.096 that the blue bank is interpreted as a determiner adjective noun. So that's pretty likely at this point, which is in fact going to come out to be correct. Is everyone understanding the way the Viterbi works at this point? Should we do the next time step? Yeah, why not? Let's, well, as people are shrugging. Let me point out a couple of things just about Viterbi before we end. Maybe I won't do the next time step. But the nice thing is that because we maintain probabilities at every state, if at the next time step we saw something Look, let's say we saw something in the next time step that just the only thing it could be was a noun. We would have preserved the ability to say that it went det, adjective, adjective, noun, right? Because there's non-zero probability at adjective here. So we haven't cut off any possibilities, but we have preserved how likely they are up to this point. And we're taking into account both the state evolution of the underlying system and the probability of the various observations and melding them together. Yeah. Any more questions? Any questions about HMMs, Frank?
I guess in this specific case,
Yeah.
If you have something that doesn't fit into your syntax because of input error for whatever reason,
Yeah.
then can you handle? I mean,
So we have an unsmoothed probability model there that has probability 0 for a lot of transitions. So yeah, so then you're like, it's an impossible input. Cannot occur. No.
I actually had to deal with the problem when I found the project. It's not like, because it wouldn't actually be a 0, it would just be a very, very, very small number, and so it would take the tally of how many times it actually occurred like that.
So if you saw it during training, when you were building your model of the language, then you'd be okay.
Yeah.
But what if you don't see it? Should you pretend to see it, like that add one smoothing trick we talked about? So I like add one smoothing. Yeah. So the Viterbi algorithm, it's awesome. It's dynamic programming. It's totally great. Now the only problem, and what's neat is that blue here, right? 0.4 probability of being an adjective, 0.4 probability here as a noun, but the grammar really disambiguated things for us. I mean, both parts of the system were doing a little bit of work for us, which I like.